Hello students, welcome to day 22 of PU2 Brahmastra Series. So today we are going to discuss a very important chapter which has a very high weightage in your PU2 examination, that is coordination compounds. Okay, so this chapter it is a very scoring topic. You need to know certain basic things, and in this lecture I am going to discuss almost 40 plus questions. Okay, so if you do this one lecture, practice all the questions, then definitely you will be able to answer all the questions asked from this particular chapter in your PU2 examination. Okay, and one more request, please join our WhatsApp channel. Link is there in the description section. So if you join there, you will be getting the PDF of these class notes and everything, so that you can prepare by your own. Okay, so that's all students. Now let's get started, and remember, you have to sit with a notebook and a pen and need to write down all the questions, and you have to practice answer with me. Okay, so yes, now let's get started. The first thing here is what is the marking scheme for this particular chapter. So coordination compounds will be asked for 11 marks, in which you will be having three marker questions, so that accounts to 9 marks, and 2 MCQs, or I can say 1 marker question, which gets you total to 11 marks, right? Now coming to the index in this particular lectures, we are almost discussing 45 plus questions in essay 3 markers, and in 1 markers I'll be giving you 10 HOTS question. Okay, now you might be thinking that MCQs are very less, and MCQ is where you find difficulty, but do not worry, before the exam we will start a dedicated MCQ series where we are going to discuss 60-70 questions of per chapter. Okay, so that will be taken care of, but now let us focus on the strengthening the core, from where you will be getting 9 marks. Let us first assure that 9 marks will be getting. Okay, so now coming to the first question here. Okay, before starting that, one very important thing here I want to tell you, that we have launched PU2 Success Blueprint Test Series. Okay, so in this test series you will be getting 12 mock tests, in which 4 part tests are there and 8 full length papers will be there. These question papers, the first test series is available from 15th of December 2024. Okay, so mark this date. From this date the first test paper will be released. Apart from this test papers, you will be getting, these test papers will be covering physics, chemistry, maths, bio or CS. You can also add Kannada to that. Okay, and you will be getting exam focused question paper based on the latest pattern and latest syllabus. You will be getting video solutions, one shot revision videos, and all your doubts will be clarified in this particular mock test. Okay, so students, do not delay it. The first test is 15 December, so before that please buy it at a discounted price of 599. If you further delay, then definitely the prices will go high, so that is why make sure that you purchase this at the earliest and make your preparation much more easier. Okay, so yes, now let us go to our first question, that is, what type of bond is ligand to metal in complex compounds? So you know the chapter name is coordination compounds. So ligand to metal is there, what type of bond? Coordinate bond. Okay, next question number 2 here. If the secondary valence in COCl3.4NH3 is 6, the solution conductivity in silver nitrate corresponds to. Okay, so now if you see, it has secondary valency is 6. That means the cobalt has 6 coordination number. So there will be, we can write CO, okay, NH3 4 is there, and I have Cl2, and then 2 Cl are outside. Okay, so now you can see what ions I will get from here. I'll get one of this complex and 2 Cl minus, right? So that is why this is a 1:2 electrolyte. Option number B is the correct answer here. Next question number 3, given that 1 mole of NiCl2.6H2O with excess of AgNO3 precipitates 2 moles of AgCl, what is the secondary valence of Ni? Now here also you can see that it precipitates 2 moles of AgCl. That means 2 chlorine will be outside. Okay, then one more thing it is given, you have to find the secondary valency, right? If I write like this, NiH2O whole 6 Cl2, right? Now you can see 2 chlorine is outside, and what is the coordination number of nickel here? 6. So the secondary valency of nickel is 6. Okay, option number D is the correct answer here. Next question number 4, what is the sum of the oxidation number of cobalt in COH2O CnEn2 2 plus and COBr2 En2 plus? Okay, so let us say the first one, we have COH2O, okay, CnEn2, okay, one second, okay, En2 and 2 plus, right? So if I calculate, this is neutral, this is -1, this is also neutral. So I can write cobalt is X, this is -1, and the net charge is +2, right? So that is X is equal to +3. Okay. Now there is one more, that is COBr2 En2, okay, 2 plus, sorry, En2 plus. Okay, one second. Okay, now if you see, let this one be X, bromine is -1, but we have 2 bromine, so it is -2. This is again 0 is equal to +1. So here also I will get X is equal to +3. Now sum of this one and this one will be +6. So option number D is the correct answer here. Okay. Next question number 5, what is the primary valence of iron in the coordination entity? This one. Okay, so you have to tell me the primary valency of iron in this coordination entity, right? So it is like this, Fe4 Fe Cn6 3, right? Now what you can think, how this coordination compound must have formed. So this compound must have formed like this. See, Fe plus 3 is there, okay, and you have Fe Cn6 4 minus. Okay, now when this one will undergo crisscross, we will get this compound, right? So I have this compound FeCN6 4 minus. I want to calculate the oxidation number. When it is asking primary valency, it is oxidation number of iron. So that is X, Cn is -1 and I have -6 here, that is equal to -4. So X is equal to +2, right? So option number B is the correct answer here. Next question number 6. Which of the following compounds has enantiomers? So if you see here, all the ligands are same, so it cannot have. Here there can be possible, here also all the ligands are same, not possible, here also all the ligands are same. Here we can have all the same ligands are, although it is same, but this has a chelating ligand, right? It is C2O4. So it is like this, okay, C2O4, and if you draw the, what I can say, mirror image, it is like this. Okay, so these two are non-superimposable mirror images, so they are enantiomers. Okay, so correct answer is option number B here. Next question number 7, linkage isomerism is seen in compounds having. So what is linkage isomerism? Suppose a metal is there, and let us take an example of Cn. Okay, so in this you can see C binds with the metal, and in the same way there can be a possibility that N is binding with the metal. So this type of isomerism is called as linkage isomerism, when two different atoms of the ligand can bind to the metal. And these type of ligands which has two donor atoms but any one binds at the one time is called as your ambidentate ligands, right? So correct answer is option number D here. Next question number 8, the compounds CONH3ClSO4 and CONH3,5SO4Cl are dash isomers. So now if you see, you ionize this one, if you dissolve this one in water, you will get one complex ion, this one, and SO4 ion, and here you will get complex ion and one chlorine ion. Because you are getting different ions on ionizing them or on dissolving them, this is called as ionization isomers. Okay. Next question number 9, which of the following orbitals does not belong to T2G orbitals? So in T2G we have dxy, dyz and dzx. In EG we have dz square and dx square minus y square. So dz square does not belong to T2G orbitals. Okay. Next question number 10, what will be the electronic configuration of D5 in terms of T2G and EG in an octahedral field when delta O is less than P? This is very important. Delta O is less than P, where P is the energy required for pairing of electrons in a single orbital. Okay, now you see delta O is less, that means what? The splitting is less. Okay, just remember like this, if delta O is less, then splitting will be less. So we will have like this T2G and EG. Okay, like this it is present. Now you have 5 electrons, so because this energy gap is very less, the electrons can easily get excited, right? 1, 2, 3, 4 and 5. So the configuration is T2G3 EG2. Okay, so we have T2G3 EG2, that is option number C. Now we will move towards the 3 marker question. We'll start from the starting. The first thing that in the lecture, in the book you have is Werner's theory, right? So let us, the first question here is state the postulates of Werner's theory. So all of you might be knowing, you need to remember these 3 points, okay? So the first point is, according to Werner's theory, in coordination compounds there are 2 types of valency, that is primary and secondary valency. Okay, this is not a point, this is an introduction point. Okay, next you need to write about primary valency, about secondary valency and about the spatial arrangement. So what are we going to write in the second point? The primary means this is your introduction point. Okay, then the first postulate will be the primary valencies are normally ionizable. Okay, primary valencies are normally ionizable and are satisfied by negative ions. The next thing, the secondary valencies are non-ionizable and these are satisfied by neutral molecules or negative ions. Okay, so the secondary valency is equal to the coordination number of the metal. Okay, this question can also be asked in the terms of difference between. Okay, so I'll be telling you in the terms of difference also. Primary valency is ionizable. Okay, secondary valency is non-ionizable. Next, primary valencies are satisfied by negative ions, right? Secondary valencies are satisfied by negative and neutral ions. Okay, secondary valency is equal to coordination number of metal. Okay, and next what we can say about another point about secondary valency is the ions or groups bound by the secondary linkages to the metals have characteristic spatial arrangement corresponding to different coordination numbers. Okay, so you can just write down the secondary valency tells about the spatial arrangement. Tells about the spatial arrangement. Okay, so like this you can write down the points. Clear? Now let us okay, now let us go to the next question, that is about your, so this is all about Werner's theory. Okay, next question is like this: FeSO4 solution mixed with ammonium sulfate solution is 1:1 molar ratio gives the test of Fe2 plus ions, but copper sulfate solution mixed with aqueous ammonia in 1:4 molar ratio does not give the test of copper 2 plus ions. Explain why. This is also very important question from your NCERT. The question is saying that if you mix FeSO4 with ammonium sulfate, okay, in 1:1 molar ratio, means 1 mole of this and 1 mole of this, then it gives the test of Fe2 plus, means after you have mixed a solution, you have prepared a solution and now you are doing some test to identify Fe2 plus ion, it shows positive test. But if you take copper sulfate and you mix it with ammonia, the same ammonia mixture if you mix in 1:4 molar ratio, you take this one 4 and this one 1 ratio, the copper ions do not show the test. Why? Okay, so that is very simple here. So that is because you see, when FeSO4, okay, is mixed with ammonium sulfate solution in 1:1 molar ratio, it forms something called as double salt. Okay, so that is FeSO4.NH4 whole to SO4.6H2O, which is nothing but your more salt. Okay, so that is FeSO4.NH4 whole to SO4.6H2O. This is formed, right? Now if you dissolve so you got this solution, right? So in the solution what will happen, these will be present in the form of ions. So you will have Fe2 plus ions, you will have NH4 plus ions and you will have SO4 2 minus ions, right? So that is what which ionizes in the solution to give Fe2 plus ions, hence it gives the test of Fe2 plus ions. So because there is Fe2 plus ions, now if you do any test of Fe2 plus, it will show positive test, right? But now what happens if copper sulfate solution is mixed with ammonium sulfate in 1:4 molar ratio, in 1:4 molar ratio, it forms a complex salt with the formula CuNH3(4) Now what happens with copper? Okay, if you take copper and this one NH4(2), it is given with ammonia, right? So if I mix this with ammonia, 4 moles of ammonia, okay, then you get a complex like this. Okay, now if you see this complex here, copper 2 plus ions are not available. Okay, this complex ion is present, but specifically or isolated copper 2 plus ions are not available. So if copper 2 plus ions are not available, it won't show the test of copper 2 plus, right? So that is the case here. The complex ion does not ionize to give you copper 2 plus ions, hence it does not give the test for copper 2 plus ion. Okay, next question number 3. On the basis of the following observation made with aqueous solution, assign the secondary valencies to the metal in the following compounds. Okay, so we have given the compounds, okay, and the moles of AgCl precipitated per mole of the compounds with excess of AgNO3. Means with this solution, if you add excess of AgNO3, right, how many moles of AgCl is precipitated? That is asked in the question. Now in the first one, okay, in the first one, if you add AgCl to this one, if you add AgNO3 to this one, 2 moles of AgCl is precipitated. That means 2 Cl will be outside the complex. So what will be the formula here? PdNH3(4) Cl2, right? So what is the secondary valency? Here you see the coordination number of Pd is 4, so the secondary valency will be 4, right? Next, here you see again 2 chlorine is 2 moles of AgCl is formed. That means 2 chlorine will be outside. So I will be writing the second formula like this. You have Ni, okay, H2O 6 and then Cl2. Okay, so again here you have 2 moles of chlorine which is present outside, and inside you have 6. The secondary valency will be 6 in this case. Okay, next PtCl4 2HCl. Here you see 0 AgCl is formed. That means there is no chlorine outside, right? So we can write it like this. Third one, we have Pt, and here 4 chlorine, and here we have 2 chlorine, so I will make it Cl6, right, like this. So there is no chlorine outside, and all the 6 chlorines are inside. All the 6 chlorines are inside. So the coordination number or the secondary valency here will be again 6. Okay, it will be again 6. Next, if you see COCl3 4NH3, here 1. That means only 1 chlorine is present outside, right? So I will be getting the formula like this. CONH3, okay, 4 NH3 is there, 1 chlorine is there, 2 chlorines will be there, 1 chlorine will be outside, and this 1 chlorine will form AgCl. So now we are having how many coordination number total? 4 plus 2, 6. That means the coordination, the secondary valency is 6. Now if you see the next one, 0, that means both the chlorines will be inside, right? So I will get the formula like this, PtCl2 NH3(2), right? I will get the compound like this. So that is why here you see the total, I can say the total number of bonds or the secondary valency of Pt or the coordination number of Pt is 4, right? So that is 4 here. Clear? Okay, let us go to the next question. Give the difference between double salts and complex. Okay, so this is very simple. Double salts will dissociate completely in water. Okay, complex do not dissociate completely. Okay, so examples you should remember: carnallite, okay, KCl.MgCl2.6H2O, then you have more salt FeSO4.NH4 whole 2 dot 6 H2O and potash alum. Okay, so these formulas you should remember of the double salt, and complex you can give any simple example. Next, question number 5, we'll go to now definitions of important terms. Okay, so the first one is explain coordination entity, ligand and coordination number. Okay, so let us see the first one. Coordination entity means what? A coordination entity consists of the central atom or ion bonded to a fixed number of oppositely charged ions or molecules known as ligands. So coordination entity means metals and ligands. Example, you can see NiCO4. In this entity, nickel is the central atom and it is surrounded by 4 carbon monoxide ligands. Okay, example is clear. Next one is ligand. So what is ligand? Ligand are the atoms or ions or molecules that can donate a pair of electrons to the central atom in a coordination compound. Okay, so here ligand CO is donating electrons to the nickel, so CO is a ligand. Okay, example of ligands can be NH3, Cl-, water. Enough examples are there. Next, what is coordination number? Coordination number is defined as the total number of ligands, okay, atoms that are directly bonded to the central metal atom or ion in a coordination complex. So if I see in NiCO4, nickel is the central atom and it is surrounded by 4 carbon monoxide ligands. So coordination number of nickel is 4, because how many ligands are there? 4 ligands are there. Okay. Next, question number 6, explain with 2 examples each of the following. Coordination polyhedron. What do you mean by coordination polyhedron? This is important. Now see, the coordination polyhedron refers to the spatial arrangement of the ligands around the central atom in a coordination complex. Okay, so coordination entity means the central atom and the ligands. Okay, but the arrangement of the ligands around the central atom is called as coordination polyhedron. Okay, so example, you see NiCO4, the coordination polyhedron is tetrahedral as the 4 CO ligands are arranged around the nickel atom in tetrahedral shape. Okay, similarly you can give, there are 2 examples, you can give NiCN4 2-. Okay, thus in this the CN ligands are arranged in the square planar shape. Okay, next coming to what is a homoleptic complex. So homoleptic complex means that type of complex where all the ligands are of same type. Okay, so you can see the a homoleptic complex is one in which the central metal atom is coordinated to only one type of ligand. Example, the same example NiCO4, you can see all the 4 ligands are carbon monoxide. Next is a heteroleptic complex is one in which the central metal atom is coordinated into different types of ligand. Here you can see the example NiCl2 H2O whole 4. So there are 4 H2O and 2 chlorine, right? Different ligands are present. So this is a heteroleptic complex. Okay. Next we'll go to question number 7. One second. Okay, next we'll go to question number 7. What is meant by unidentate, didentate and ambidentate ligands? Give 2 examples of each. Okay, so now coming to unidentate. Okay, so first let me explain you what is denticity, then we'll talk about unidentate. Now see, metal is there, ligand is there. Okay, now ligand can bind to the metal. Okay, if ligand binds to the metal through only one atom, or if I say that ligand forms only one bond with metal, then its denticity is 1. So we can explain, how can we explain denticity? Denticity is the number of bonds formed by one ligand with the metal. Okay, so if unidentate ligand means if a ligand forms only one bond with the metal, then it is unidentate. Now if you have a ligand, okay, and it is forming 2 bonds with the metal, then it is a bidentate. If you have a ligand and it is forming, like I can say 6, there is one ligand and all these 6 bonds are formed by one ligand, then it is called hexadentate ligands. Okay, so denticity is what? Denticity is the number of bonds formed by one ligand with the metal. Okay, so I hope now it is clear what is unidentate. So one second. Okay, so here if you see a molecule or ion which has only one donor atom to form one coordinate bond with the central metal atom is called unidentate ligand. It has only one atom which can form bond with the metal, or it can form only one bond with the metal, then it is unidentate ligand, right? Example, Cl minus and NH3. Bidentate, a molecule or an ion which has two donor atoms to form two coordinate bonds with the central metal atom is called didentate ligand. Example, NH2, 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 CH2, CH2, NH2. So I want to show you this ligand. So this ligand is like this. This ligand is like this: CH2, CH2, NH2, and NH2. Right. So what happens? The lone pair present on both the nitrogen forms bond with the metal. Okay, so at a time it is forming two bonds with the metal, so that is a didentate ligand. Okay, next coming to examples, ambidentate ligand. So during MCQ I have already discussed what is ambidentate. So now ligands which has two different donor atoms and either of the two ligates in the complex is called as ambidentate ligand. Means it has two donor atoms. Okay, now you see didentate, this one also has two donor atoms and two of them form bond with the metal at the same time. But ambidentate has also two donor atoms, but only one will form at a time. For example, if I have Cn, okay, so M will form bond, is forming bond with C. At that time N will not form. There can be another complex where N is forming bond but C is not forming bond. But there are two donor atoms but only one will form bond at the same time. That is called as ambidentate ligand. Example, NO2 minus, Cn minus, or you can write SCN minus. Okay, clear? Next, let us go to question number 8. What are chelating ligands? This is also very important. So when a di or a polydentate ligand uses its two or more donor atoms simultaneously to bind a single metal atom, it is called a chelate ligand. So now what happens? Suppose you have a metal and you have this ligand. Okay. Now this is forming bond with the metal. So when a bidentate or a polydentate ligand forms a bond with the metal, we get a cyclic structure, right? So this cyclic structure is called as chelate. This type of ligands which can form a cyclic structure is called as chelate ligand. Okay, and what is the speciality about that? Such complexes are called as chelate complexes, and they tend to be more stable than similar complexes containing unidentate ligand. Okay, so if there is a chelation, then definitely the stability increases. Okay. Next, question number 9, specify the oxidation number of the metals in the following coordination entities. Okay, so I will be telling you how to calculate the oxidation number. So here are whichever ligands are used here, I will be telling you their oxidation states. Okay, so let us first do that. So cobalt is the central metal atom, oxidation state of water is 0. Okay, Cn is -1, En is also a neutral ligand, so it is 0. Cl is also -1. Okay, then NH3 is 0. Okay, Br, chlorine, bromine, all are -1. Then we have, I think I have completed, yeah, and potassium is +1. Okay, now let us do this question. You have to calculate the oxidation state of the metal here, right? That is cobalt oxidation state you need to calculate. We don't know that, let it be X. Okay, so I'll put 1, let it be X plus. Water is 0, right? So that will be 0 plus Cn is -1, so I have now -1. Okay, then En is also 0, so again 0, and this all should be equal to the total charge of the complex, that is 2 plus. So if I now solve, I'll get X is equal to +3, right? So the charge of cobalt here is +3. Next, if I see PtCl4 2 minus, okay, PtCl4 2 minus. Okay, so again we can check, this one is X, chlorine is minus 1, so we have minus 4 is equal to minus 2, so X is equal to plus 2, right? So this is your X is equal to plus 2. Next you have Cr NH3 whole 3 Cl3. Okay, so you have Cr NH3 whole 3 Cl3. Now again Cr is X, NH3 is 0, Cl3 is minus 3 and that is 0. Okay, so X is equal to plus 3. Clear? So this is plus 3. Next, coming to question number 4. Okay, we need to find for cobalt again. So let cobalt be X. Next you have 2 bromine. Each bromine charge is minus 1, so 2 bromine will be minus 2, right? Next you have En2, so that is 0 and the net charge is plus 1. So I will get what? X is equal to again plus 3 here, right? Okay, next if I see the fifth one, you see K3. So potassium is plus 1, there are 3 K, so that is, if there is 3 K, so the total charge is plus 3. Okay, then Fe is X, Cn is minus 6, okay, is equal to 0. So X will be equal to plus 3, right? That is equal to plus 3. Clear? So these are the how you need to calculate the oxidation states of the central metal atom in the complexes. Okay. Next, now we will move towards nomenclature. Very important topic. Questions are definitely asked from nomenclature. Every year it is asked. So here by doing these questions we will revise the rules also. Okay. So the first thing is, using the IUPAC norms, write the formulas of the compounds. First compound is given tetrahydroxido zincate 2. Okay. So first one if I write, it is very simple. Tetra means 4. Hydroxido means OH. Okay, then what is the metal? Zincate. So zinc should be at first written, the metal should be written first, then OH4. Okay, next here you need to calculate the charge of the complex. Now zincate 2 is given, that means the charge of zinc is 2. Each OH charge is minus 1. Okay, remember OH charge is minus 1. So there are 4 OH, so that means minus 4, that is equal to minus 2. So what is the charge of the complex? Minus 2. Okay. Now whenever you find that the metal name is ending with ATE, okay, metal name is ending with ATE, that signifies that it is a negative ligand. Okay, sorry, it is a negative complex. The charge of the complex should be negative, or we call it as anionic complex. Okay. Next, let us see the second one, that is hexaamine cobalt 3 sulfate. Okay, so first of all, if you see hexaamine cobalt sulfate, okay, cobalt is there, so first it should be written cobalt, then you have hexaamine, that means 6 times amine should be present. Okay, and outside it is sulfate. Okay, now how to write down the correct formula of the complex? Now see, cobalt, what is the charge given? 3, right? And we know neutral ligand, so this will be 0, so total charge is plus 3, right? This is plus 3. Okay, sulfate charge you should know, it is minus 2, right? Then what will happen? There will be a crisscross here, right? And after crisscross, what formula I will get? That should be written. So after crisscross I will get CONH3 whole 6 2 SO4 3. Right, this is the correct formula. Clear? I think that is correct. Yes. Now let us move towards the next question. Let us move towards the next question, third one, that is potassium tetrachloridopalladate 2. Okay, so first is potassium, so we will write potassium, then bracket. In that, what is there? Tetrachloridopalladate. So palladium is the then, and then you have tetrachlorido, so 4. Now here also you need to check the charge. Now see, palladium is given plus 2 charge, right? So that is plus 2. Chlorine is minus 4, so I'll get minus 2. This is minus 2, right? And potassium is plus 1, we know. So if I do crisscross, what I will get? After crisscross only you should be writing the final formula. So if I do crisscross, I will get K2PdCl4. Okay. Now coming to question number 4 here. potassium trioxalato chromate 3. Okay, so first we have potassium, then you have chromate Cr, that means trioxalato. Oxalato is C2O4. Okay, 3. C2 trioxalato, this one is there. Now let us calculate the charge. Chromium charge is +3. Okay, now C2O4, each C2O4 charge is -2. Okay, so remember here C2O4 charge is how much? -2. Okay, each C2O4 charge is -2. So there are 3 C2O4, that means the total charge here will be -6, right? So I will get the charges -3. This is +1 and this is -3. Now if I do crisscross, I will get K3 Cr C2O4 3 whole. Okay, so I will erase this. Yeah, we will get this as the formula for the fourth one. Okay, next if I say fifth one, diamine dichlorido platinum 2. Okay, so you can see first metal is there, platinum. Okay, then you have diamine and dichlorido. So diamine means NH3 whole 2, dichlorido means Cl2. Okay, so 1 second. Yeah, dichlorido in Cl2 is there. Okay, now if you see, this is platinum. Okay, platinum charge is given to you +2. Okay, NH3 is 0, chlorine is -2, so that is 0. That means there is no charge on this particular compound and it is a neutral complex. Okay, clear? So we have these 5 formulas for the structures. You can check the answers once again. Okay, let me get side, right? Okay, now let us go towards the next question where you have to do similar questions. Okay, some more practice. So next one is hexaamine platinum 4. Okay, let us do this one. Hexaamine platinum 4. This is very simple, I think. Okay, you have hexaamine platinum 4. So platinum is there, hexaamine is there, right? Platinum 4 is there, that means this charge is 4, this is 0, so this is +4. Next I have 7th one, potassium tetracyanidonickelate 2. Okay, so let us first write potassium, then we have tetracyanidonickelate. So you have nickel, tetracyanido. Okay, tetracyanidonickelate. Okay. Now if you see what is the charge of nickel that is given to you, +2. Okay, this is -4, so I will get -2. This is -2 and this is +1. So if there is a crisscross, right, what I will get, this 2 will come here, right? So after crisscross, this 2 will come here. Okay, this will be the formula. Let us see the next one, that is okay, next one is your 8th one. What is it? Tetrabromido cuprate 2. Okay, so that means copper is there and 4 bromine is there. Okay, now if you see what is copper charge, that is +2, and here you have 4 bromine, that is -2. So this is -2. Okay, clear? Next is 9th one, pentaamine nitrito O cobalt 3. This is important here. Okay, now pentaamine for first metal is cobalt. Okay, next you have pentaamine, so I'll put NH3 whole 5. Nitrito O is written like this. Okay, nitrito O is written like this, and then the charge we need to calculate. So cobalt charge is 3, this one is 0, and nitrito NO2 is -1. Okay, so I will get +2. So this is +2. Okay, next question number 10, pentaamine nitrito and cobalt 3. Okay, so let us try again the same thing. You have pentaamine cobalt, pentaamine is there. Okay, next nitrito N is written like this, NO2 minus. Okay, and the charge will be same, you will get +2. Okay, clear? So these are the 10 questions how to write the structure from the IUPAC name. Now what we are going to do, question number 11, we will be writing the names of the compound based on the structure. Okay, let us start with the first one. So if you see, first step is you should calculate the oxidation state of the metal. Okay, so here if I see, you can see what will be the oxidation state. So let us do like this. We have CO NH3 whole 3, sorry, NH3 whole 6 and Cl3. So the oxidation state of cobalt is X, this is 0, this is minus 3, this is 0. So what will I get? The chlorine I have taken minus 3, the total charge is 0. So X is equal to plus 3. Okay, clear? So now if I want to write the name, first always we need to write the cation name. Okay, so cation is a complex, and inside the complex you should first write the name of the ligand. So we have the name hexa, 6 ligands are there, amine. Okay, next is cobalt. Okay, now if you see the charge of cobalt is plus 3, right? So that should be written in Roman numbers. Okay, and outside we have chloride. Okay, this one is called as auxiliary ion. Okay, sorry, this one is called as counter ion. Okay, the outside ions are called as counter ions, and in counter ions you should not mention any number like trichloride or 3-chloride, nothing like that. Okay, the counter ion should be just written in the name. Okay, next if I see question number 2. Okay, CONH3 whole 4 Cl NO2 Cl. Okay, so let us write down, it is CONH3, okay, 4 Cl, then I have NO2, then I have Cl. Okay, so now if I want to write the name of this particular compound, so you can see again this is the cation, this is the anion, so cation should be named first. Inside cation the ligands should be named first. Now when you have more than one type of ligand, you should name it according to the alphabetical order, right? According to alphabetical order you have to name it. So here if you see, this is amine, this is chlorido, this is nitrite. So the order should be in this way. So first I will write tetraamine, okay, 4. Next we have 1 chlorido, so chlorine is written as chlorido. Okay, then I have nitrito N. Okay, so this is written as nitrito N. Okay, you can see here like this, nitrito N. Okay, then the metal here is cobalt. Okay, now you can check the calculation, the oxidation state of cobalt here. Let this be X. Okay, this is 0, this is minus 1, this is also minus 1, this is also minus 1. So X is equal to plus 3. Then outside we have chloride. Okay, so that will be the name. Now let us do the next question, that is third one. Okay, so here you see we have nickel, then you have NH3 and then chlorine. So first I will write, so this is hexaamine, right? Hexaamine. Next is nickel, right? Now you see the charge of nickel, this is X, this is 0, this is minus 2 is equal to 0, so X will be equal to plus 2. So nickel is in plus 2 state. Okay, outside we have chloride. Okay, done. Now let us do some more questions. Let us take this question here. PT NH3 whole 2 Cl NH2 CH3 Cl. Okay, so now first one if you see, okay, you have PT NH3, then you have Cl, then you have NH2 CH3, okay, then you have Cl outside. Okay, PT NH3 whole 2 is there. Okay, so here also you should name it alphabetical order. So first I need diamine, right? There are 2 amines, so that will be diamine. Next you have chlorido. Okay, next this is methylamine. Okay, next the name of the metal, that is platinum. Okay, inside this you need to write the oxidation state. So this is X, right? This is minus 1, these all are 0, this is also minus 1. So X minus 1 is equal to 0, so that means X is equal to plus 2. So Roman number plus 2, outside I just need to write chloride. Okay, similarly question number 2 here, MnH2 whole 6 2 plus. This is also very easy one, Mn H2O whole 6 2 plus. So here you should know that if water is a ligand, okay, the name used is aqua. We used aqua. So how many water is there? 6. So hexa aqua. Okay. Then you have manganese. Hexa aqua manganese. Spelling, I think I did wrong. 1 second. Yeah, manganese charge is 2. So 2. Okay. Now third one. Third one is what? COEN3 whole 3 plus. This is important one. Okay. So whenever this ligand comes, okay, En, and you want to write the number, we do not use bi, tri, dri, we do not use. If En is there, you need to use the word bis for 2, okay, tris for 3, and tetrakis for 4, okay. So now we have 3, so I will use tris, okay. So this is tris, and the name of the ligand is ethane 1,2-diamine, okay, ethane 1,2-diamine, tris ethane 1,2-diamine, then you have cobalt, and the charge is 3, okay, because this is also a neutral ligand, so 3 plus you will get cobalt 3, okay. Next, question number 13, let us do some here. So the first one is TiH2O whole 6, again very easy, you can see hexa aqua, okay, then you have titanium, right, charge is 3, okay. Next, second one, NiCl4 2 minus, this is important. So you have here tetrachlorido, okay, tetrachlorido nickelate. Yeah, now see, whenever it is an anionic complex, okay, if the charge of the complex is negative, it is an anionic complex, the metal name will end with ATE. So this is a negative complex, so it is nickelate. And what is the charge of nickel here? So this is X, chlorine is -1, and 4 chlorine means -4, that is -2 is equal to 0. So I will get, sorry, 1 second, okay, this is equal to -2, right? Yeah, equal to -2. So I will get X is equal to +2, that is like this. Next, third one, if you see NiCO4, so it is tetracarbonyl nickel, okay, tetracarbonyl nickel, oxidation state of nickel is 0 here, okay. So that is how you need to write the name of the compounds. I hope this much practice is enough. You can do more questions from the exemplar, from the NCERT examples also is there. You can take those questions and practice some more, okay. Now let us move to question number 14 about isomerism. So isomerism is of 2 types, right. First, let me give you a brief of isomerism. So you have one is like stereoisomerism, okay, stereoisomerism and structural isomerism, okay. So these are 2 categories. Under stereo you have geometrical and optical, okay, and under structural you have linkage isomerism, then you have ionization, you have coordination, and you have solvation, okay. So you need to remember at least these 4 ionization definitions and examples, okay, that is mandatory. And here also you have to do these questions. So I will be telling you the first question, explain the geometrical isomerism with CN coordination number 4 with example, okay. So now geometrical isomerism, I told you, is a part of stereoisomerism, right. So in geometrical isomerism we have again 2 types, one is CN4 and coordination number 6. In coordination number 4 we have cis and trans geometry, and same in coordination 6 also you have cis and trans, and another is facial and meridional. These type of geometrical isomers are there, okay. And CN4 we have 2 geometries, one is tetrahedral and another is square planar, okay. So in case of square planar you can have cis and trans, but in tetrahedral there is no geometrical isomerism, okay. So let us see this one then. So as I told you, in square planar complexes, okay, you can have cis and trans geometry. The formula is mx2l2. The two ligands X may be arranged adjacent to each other in a cis isomer or opposite to each other in the trans isomer. Then other square planar complexes of the type MABXL, okay, means where all the four ligands are different, where ABXL are unidentate ligands, so 3 isomers, that is 2 cis and 1 trans. Okay, so this much you should remember for your geometrical isomers. Okay, so if I give an example of this one, you have PTNH3 whole 2 Cl2. Okay, then what will be the cis geometry? You have two NH3 groups on the same side, chlorines on the same side, and the trans one will be NH3 on the opposite side and Cl on the opposite side. Okay, so this is cis and this is trans. Clear? So what I want to say, for geometrical isomerism, square planar complex means if coordination number 4 is there, okay, then only square planar complexes will show geometry. MAX2L2 type will have this 10 and another MABXL type will have 3 isomers, 2 cis and 1 trans. Okay. Next, question number 15, draw the cis and trans isomers of the following complexes with coordination number 6 of the type ML4X2. So if I have ML4X2 and I want to draw the cis and trans, so it is like this. All the L ligands are on the one plane and X is like this, this is trans. Okay, and if I want to draw cis for this one, you just take anything like this, X, X, L, L. Okay, all are cis to each other, so this is cis isomer. Next you have MLL2XS2. So this LL represents a bidentate ligand. Okay, so any type of this if you find, okay, that is like this, MLL2, right? So you have like this, MLL2X2, this is the trans one, and here if you write like this and do like this, okay, so this is the cis one. Okay, let me just make this one second. Okay. This is cis, this is trans. Next you have ML3X3, they do not have cis and trans, they have facial and meridional. Okay, so if you have M, okay, these are the 3 sides. Okay, the one side you take all X, okay, another side you take all L, this is called facial. Okay, and any other configuration apart from this, okay, if you have L here, X here, X here, X here, L here, L here, okay, this is your meridional. Okay, clear all the examples? Now let us do next question. Why is geometrical isomerism not possible in tetrahedral complexes? Okay, so as I told you, in coordination number 4 we have 2 geometries, one is tetrahedral, another is square planar. Okay, so square planar has again 2 types, one is MA2B2 type, okay, and another is MABX type. Okay, so this one will show cis and trans geometry, 2 you will find, and here you will find 3, and 2 is cis in this one and 1 is trans. Okay, but in tetrahedral there is no geometry, no geometrical isomers possible. Okay, the reason for that is the tetrahedral complexes do not show geometrical isomerism because the relative positions of the unidentate ligands attached to the central metal atom are the same with respect to each other. Okay, so that means the positions are almost same. Okay, here that is not like one, here you can see 2 are on one side, 2 are on another side, it is not like that, all are equidistant. So that is why tetrahedrals do not show geometrical isomerism. Okay. Next question is about optical isomerism. What do you mean by optical isomerism? So now here you can see optical isomers are the mirror images that are non-superimposable on one another, and these are called as enantiomers. Okay, the molecules or ions that cannot be superimposed are called chiral. So this is that you know chirality in your haloalkanes chapter also. Now the 2 forms are called as dextro and levo depending upon the direction of the plane polarized light. Okay, if they rotate clockwise we call it D, if they rotate anti-clockwise we call it L. dextro and levorotatory. So this is all about optical isomerism. Now question, this is important question, draw the optical isomers of PTCl whole to En2. Okay, so now if you see, this is of the type MLL2, okay, B or A2, like this. So here let me write down three things. If you have MLL2, okay, means this is a bidentate ligand and X2. Okay, this one will have two geometrical isomerism, cis and trans. Okay, the cis form of this one, okay, is optically active. Optically active. Okay, clear? Next, okay, so now let us, and one more thing, that is MLL3 type. Okay, for this there is no geometrical isomers, okay, only optical isomers. Only optical isomers are present in this type. Okay, now let us, you can see here also the coordination number is 6, because here you see each ligand coordination number is 2. So 2 ligands means 4 plus 2 6. Here each ligand coordination number is 2, 3 ligands means total is 6. Okay, now let us do this question. You have to draw the optical isomers of this one. So you know, if this type of is there, only the cis one will be optically active. So first I will do the cis isomer. So PT, I will write like this. Sorry. Okay, so this is En, this is En, okay, this is Cl and this is Cl. Okay, this is the cis isomer. Now if I want to draw the mirror image of this one, I will get PT. This one En, this one is En, this is Cl and this is Cl. Clear? So these are the optical isomers of this one. Next, COEN3 whole 2 plus. So that is like this. You can see you have like this En, En and En. Okay, and if mirror images, if you do, it is like this. You get like this En, En and En. You can draw it little nicely. Okay, so these two are the non-superimposable mirror images and optical isomers. Next question, out of the following two coordination entities, which is chiral? Okay, so now if you see cis one, CrCl2 OX whole 2 and trans one, I told you if the OX is also a bidentate ligand. Okay, so if you have a bidentate ligand, then the cis form will be optically active, then definitely this is optically active. Okay. Next question number 19, how many geometrical isomers are possible in the following coordination entities? Okay, so if you see this one, CrC2O4 whole 3, CrC2O4 whole 3. Okay, so this is what type? This is of the type MLL whole 3, right? And for these type of ligands, there is no geometrical isomers. No geometrical isomers, right? So that is why this has 0. Next, CONH3 whole 3 Cl3. So if you remember, this is of what? CO MA3B3 type, right? This is MA3B3 type, and in this type we have facial and meridional type of geometrical isomerism, right? So I can draw that and show you. We have CO NH3 whole 3 and Cl3. So I will put Cl, Cl, Cl here, NH3, NH3 and NH3 here. Okay, now you can have another like this, CO, okay, and CO, this is facial, and you can change the configuration like this, NH3, Cl, 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 NH3 and NH3. Okay, so this is your meridional. Okay, clear? Next question number 20, draw the structures of optical isomers of this one. Okay, so the first one is CrC2O4. So this is, you can see, MLL whole 3 type, right? So that will have only optical isomerism. So you can draw Cr. Here you have like C2O4, I can write like this. One second. Yeah. So just put oxygen is the what which binds, so we can do like this. Okay, and the mirror image of this one, 1 2 3 4 5 6. this, clear. Next you have PtCl2En2. Now this one is what? Of the type MLL type. Okay, if this type is there, I told you the trans one will not show optical isomerism, the cis one will show. So for the second one we have to first draw the cis isomer. So PT, you have En, okay, here we will do En, and here you have Cl and Cl. Okay, now the geometrical, I mean the mirror image of this one, PT, we have like this, N, Cl, Cl. Okay, clear? This is done. Next you have Cr NH3 whole 2 Cl2En. Okay, this is a good question. Cr NH3 whole 2 Cl2En. Okay, so let us see what is the structure. You have Cr NH3 whole 2, okay, then we have Cl2 and En. Okay, so now if I draw this structure, I can draw the structure like this, where I have like this is En, okay. Next I have NH3 here, NH3 here, Cl here, Cl here, okay. Another structure I can draw for this one is where I will take the same En here, okay, NH3 here, Cl here, then Cl here, then NH3 here and Cl here. Okay, you can see here Cl were coming together, NH3 was coming together, now it is coming opposite to each other. Okay, next another I can do here is Cr. Here I have taken En. Okay, now NH3 and NH3 are trans to each other, and then I have chlorine cis to each other, and the opposite of this one will be, you take En here, right, Cl here, Cl here, NH3 here and NH3 here. Okay, now if I draw the mirror images of each of them, okay, and none of them will be superimposable. If you see this one, if I draw, this one will be NH3, this will be Cl, this will be NH3, this will be Cl, and here it is En. Okay, so now you can similarly draw the mirror images of all the four, and none of them are superimposable. So you will get total 8 isomers for this particular compound. Okay, next question number 21, draw all the isomers, that is geometrical and optical, for the following. Okay, so now if you see the first one is COCl2En2, right, that is plus charge. So this is of type Ma2LL2, right. Now here if you remember, the cis one will be having optical isomers, and trans one will not have any isomer, right. So if I just do first the geometrical isomers, I'll get cis and trans. So let me draw first trans one. Okay, so this is the trans form. Okay, next if I draw cis one, so it will be Cl, Cl. Okay, so this is the trans and this is the cis. Now the cis form will have what? Optical isomerism, I mean the mirror images. It is Cl, Cl, En, En. Clear? Next if I see second one is what? CONH3Cl En whole 2. Okay, so this one is one second, yeah. So we have like this structure, En twice is there, right? So you can have like this En twice, one NH3 and one Cl, right? So this is your trans one. Now we can draw cis for this one, CO. You have En here, you have En here, you have NH3 here and Cl here, right? So this is the cis form, and the cis form will be optically active. So you can, so total 3 isomers, here we will get 3 isomers, right, because this one will also have that mirror image will be optically active. Sorry, here it is NH3 and here it is Cl. Now this one we have just drawn, right? Question number this 3 was this one, and here you will get total 8 isomers. Clear? Okay. Next question number 22. Write all the geometrical isomers of PT, NH3, Br, Cl, pyridine. So this is of the type M, A, B, X and L, right? So in this type we have 3 isomers, okay, 3 isomers, 2 cis plus 1 trans, okay. So let us draw them. So now if you see, this chlorine and bromine are of similar ligands, like they both are type halogens. So what we can do is we can keep them as like what is the metal here, PT, okay. So one second, yeah, so we have PT. You can take chlorine and bromine on the opposite side, okay, and you have, so one second, we'll draw it in the square planar shape. Yeah, so I have PT, here you have NH3 and chlorine and bromine are on the opposite side, and then you have what is pyridine, okay. This is one possibility. Here chlorine and bromine are opposite, this is trans, okay. Next you will do one where chlorine and bromine are cis. So I'll keep bromine here, I'll keep chlorine here, and we have NH3 and pyridine, okay. This is done. One more, this is your cis, okay. And one more we can do here is I can take chlorine here, bromine here, okay, and these two other sides I can take like NH3 and pyridine. So you can see here adjacent to chlorine pyridine was there, now adjacent to chlorine NH3 is there. Here adjacent to bromine NH3 was there, here adjacent to bromine pyridine is there, right? So this is also cis, this is also cis. So total number of isomers is 3, 1 is trans and 2 are cis, okay. Next question number 23, explain linkage isomerism. So this is very easy question. Linkage isomerism arises in a coordination compound containing ambidentate ligand, okay. So whenever you have ambidentate ligand, NO2 is there, its linkage isomerism will be NH3 whole 5 ONO then Cl2, okay. Next, ionization isomerism, when you get different ions from a complex, right? The form of isomerism arises when the counter ion in the complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion, okay. So you can see bromine is the counter ion, it can replace sulfate and sulfate can become the counter ion now. So this type of isomerism is called as ionization isomerism. Solvation isomerism, solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal atom or merely present as free solvent molecules in the crystal lattice. So you can see here example, CrH2O whole 6 Cl3. Now what happens, this chlorine comes out, one chlorine is replaced and hydrogen goes out, okay. So that is solvate isomerism. Solvate isomerism you can easily identify when you have water molecule. Okay, explain the coordination isomerism with example, okay. So coordination isomerism is the type of isomerism arises from the interchange of ligands between the cationic and the anionic entities of different metal ions present in a complex. So these are two, you can see two complexes are present. If you just with cobalt ammonia is there, with chromium cyanide is there, you can just exchange the ligands. So with cobalt you have now cyanide and with chromium you have ammonia. So that is called coordinate isomerism, okay. Next, we'll go indicate the type of isomerism exhibited by the following complexes and draw the structures for these isomers. Okay, so first is you can see CrH2O whole 2 C2O4 whole 2. Okay, so if you remember this one, it is of the type M LL whole 2 X2, right? So I told you already this will have one trans, the cis form will have the optical isomerism, right? So how will this one look? So if I draw the first one, so it is Cr, then you have oxalate ions, okay, and then you have H2O, okay. This is the trans form, one second, okay. So this is the trans form, its cis form will be like this, sorry, Okay, the cis form will be you have Cr, then you can put like this, okay, and you have H2O and H2O. Okay, this is clear. So now this one you can draw the mirror image and you will get its optical isomers. Okay, next here if you see COEN3, okay, so that is of the type COEN3. Just draw the starting letter of the ligands. Okay, so this is the one form and the optical isomer will be of the opposite side. So you have like this one and this one. Okay, next one is CONH3 NO2 NO3 2. Okay, so this will not have any optical isomerism, but here you can see there can be a linkage isomerism possible. Okay, and then you can do ionization isomerism also. Okay, next in this one PT NH3 H2O Cl2. So here we can have one is cis and trans, we can have PT Cl on the same side, NH3 and H2O we can have, right, and you can have trans, that is Cl on the opposite side, NH3 and OH2 you can have, right, clear. So these are the isomers that are possible. Next is explain. So now we'll go to bonding, and first is valence bond theory. So what is happening in valence bond theory? I think you have already studied in your chemical bonding chapter also. So valence bonding theory means, according to this theory, the metal atom or the ion under the influence of the ligands, okay, can use its N-1d, Ns, Np or Ns, Np and Nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planars and so on. These hybridized orbitals are allowed to overlap with the ligands. So basically what is saying that when you have a metal and ligands are approaching towards the metal for bond formation, the orbitals of the metal will undergo hybridization to give you different new hybrid orbitals which can overlap with the orbitals of the ligand. See, metals orbitals, okay, will undergo hybridization. When it will undergo hybridization? When the ligands are approaching, okay, and these hybrid orbitals will overlap with the ligand orbitals. Okay, so that is all about valence bond theory. Next is question number 9. Explain the hybridization, magnetic property and geometry of CONH3 6 3+. Okay, so I will do this one and I'll give you 3 questions homework, you need to solve it. Okay, so the first step here is you need to write, okay, I will not write in this way, I'll write the answer directly, but you have to follow the same format for 3 other compounds that I'll give you. Okay, so what you have to write, first is cobalt oxidation state in this is +3, right? So what will be its electronic configuration? It is 3d6. Okay, so we have like this. Okay, one second, 3d6. Okay, so if I draw 3d6, it is like this, 3d6. We have d 5 orbitals, 1 2 3 4 and 5, 1 2 3 4 5 and 6. Okay, and after that we have 4s and 4p. Okay, this much you have to write in the first time. Next, you know NH3 is a strong field ligand, so what it will do? It will do pairing. So here you have to write NH3 is a strong field ligand, so pairing of electron takes place. Pairing of electron takes place. Okay, now you have to show the pairing. So 3d6 we have. Okay, so now if these all electrons will pair up, so we will get like this a configuration. Then you have 4s and you have 4p. Okay, so now what happens? Next point you have to write or you can just write down, you can show like this, D2sp3 hybridization has taken place. Okay, now what you can do, this D2sp3 hybrid orbitals, in this D2sp3 hybrid orbitals we will get how many orbitals of combined, 1 2 3 4 5. So I will get, sorry, 1 2 3 4 5 6, so we will get 6, 1 2 3 4, we will get 6 D2sp3 hybrid orbitals. Okay, now what is the ligand present here, NH3, so NH3 will donate electrons on this. Okay, you can draw like this. Okay, now you talk about the hybridization. Hybridization is D2sp3. Magnetic property, there is no unpaired electron, so it is diamagnetic. Okay, and next the geometry, because coordination number is 6, right? Coordination number 6 means geometry is always octahedral. Now similarly you have to practice for 3 another compounds, very very important. First one is COF6 3 minus. Okay, next is your NiCl4 2 minus, and the fourth one is NiCN4 minus. Okay, COF6 3 minus, NiCl4 2 minus, NiCN4 2 minus. Okay, these 3 compounds you have to practice in the same way. Okay, next give 3 limitations of VVT. You can write any 3. It involves a lot. You can write down the second point here. It does not give quantitative interpretation of the magnetic data, does not explain the color exhibited by the coordination compounds. Next, it does not tell you anything about the stability of the compounds. Any 3 points you can write down from here. Okay, next coming to 31 question number, that is crystal field theory. So explain the crystal field theory. So here also you should be very very clear, understand what is crystal field theory. So see, the crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic. Okay, now ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. The 5d orbitals in an isolated gaseous metal atom have the same energy and they are degenerate. The 5d orbitals have the same energy, but when ligand approaches to this metal, these d orbitals energy changes. Okay, that is what is crystal field theory. This degeneracy is maintained if a spherical symmetrical field of negative charges surround the metal. However, when this negative field is due to the ligands, okay, it becomes asymmetrical and the degeneracy of the d orbital is lifted. It results in the splitting of the d orbital. Okay, so you need to write point number 1, point number 2, and you can write point number 3 and 5. Okay, next is d orbital splitting for octahedral. You know this one you have to draw with the levelings. You should know first it get like the energy levels are risen, and then you have T2G and EG level. Okay, so you have to practice this diagram properly. Similarly, you have for tetrahedral, the opposite thing here happens. Here it is E at the bottom and T2 at the top, and here you remember in tetrahedral there is no G is used, okay, only E and T2, but in your octahedral we have T2G and EG, right? Okay, next question number 34. What is the spectrochemical series difference between weak field ligand and strong field ligand? So a spectrochemical series is the arrangement of the common ligands in the increasing order of their crystal field splitting energy. Okay, how much a ligand can split the d orbitals, based on that the ligands are arranged. That series is called as spectrochemical series. Next, the ligands present on the right hand side of the series are strong field ligands, while that on the left hand side are weak field ligands. Okay, the strong field ligands cause higher splitting in d orbitals than the weak field ligand. Okay, like for example, you see you have 5 d orbitals degenerate. Okay, now a strong field ligand is approaching, then how the splitting will be? Here 3 and here 2, this will be the splitting. Now if a weak field ligand is approaching, then the splitting will be very less. Okay, so this is called as crystal field splitting. In case of strong field there is more splitting, in case of weak field there is less splitting. Okay, next, what is crystal field splitting energy? How does the magnitude of delta O decide the actual configuration of d orbitals in the coordinate entity? Okay, this is also very important question. So when ligands approach a transition metals, the d orbitals split into two sets, one with the lower energy and the other with the higher energy. The difference in between the two sets of the orbitals is called as crystal field energy. Now how does it decides the d orbital configuration? So here if you see, if delta O, now see, if this crystal field splitting is less, okay, so d1, d2, d3 will be written like this. Now when d4 comes, because the splitting is less, this d4 electrons go here, d5, then d6, d7, d8, d9 and d10. But if the same splitting is in case of a strong field ligand, okay, d1, d2, d3, okay, here also d1, d2, d3. But next when d4 comes, because this energy is very high, d4 cannot go here, right? What does d4 do? It pairs up here, d4, d5, d6. After that d7, d8, d9, d10. Okay, so that is what it is given. If delta O is less than P, delta O less than P is this one, okay. The fourth electron enters one of the Eg orbital, okay, 1, 2, 3, 4. Giving rise to the configuration of T2G3 Eg1. But if delta O is greater, this splitting is very high, it becomes more energetically favored for the fourth electron to occupy a T2G orbital with configuration T2G4. Okay, so we'll talk about for example D4 configuration. Okay, see, if I have a strong weak field ligand and a strong field ligand, okay, so in strong weak field ligand splitting will be less, so D1, D2, D3 and D4, and here D1, D2, D3, because this gap is very high, it will be D4 here. Okay, so that is how it will decide. Next, give the oxidation state, d orbital occupation and the coordination number of the central metal atom in the following complexes. Okay, so oxidation number you can see, you can easily calculate now. For cobalt it will be +3. Okay, coordination number here is 6. Okay, next d orbital. So cobalt, if it is in +3 state, right, what is the configuration? D6 configuration, and the electronic configuration will be T2G6. Okay, next second one, if you see, you have COF4, okay, and cobalt charge here is +2, and the what I can say, the coordination number is 4 fluorine, right, and the configuration is D7. Fluorine is a weak field ligand, right, so first the weak field ligand means splitting will be less, okay, and I want to write D7, so it will be like this. See, 1, 2, 3, 4, 5, then 6 and 7. So what I'll get here? T2G5 and Eg2. Okay, next third one is CrCl2 En2Cl. So if you see here, chromium charge is +2, right, or +3, sorry, chromium charge is +3, and what is its coordination number? Here 2 and here 2. Okay, coordination number is 6, so here 4 and here coordination number is 6, and the configuration is D3. So for D3 it is always T2G3. Okay, next fourth one, if you see, we have Mn2+. Okay, Mn2+, the configuration is D5 and it is T2G3 and Eg2, because water is also a weak field ligand here. Okay, next CrNH3 6+ is paramagnetic while NiCN4 is diamagnetic. Explain why. So CrNH3 whole 6 3+ has D2sp3 conf hybridization with 3 unpaired electrons. Okay, you can draw the valence bond diagram and you can see it has 3 unpaired electron, so it is it is paramagnetic. Okay, so here a small mistake, so it is paramagnetic. Now if you see, NiCN4 2- has dsp2 hybridization and no unpaired electrons are there, so that is why it is diamagnetic. Okay, next question number 38. NiCl4 is paramagnetic while NiCO4 is diamagnetic, though both are tetrahedral. Now NiCl4 has sp3 hybridization and 2 unpaired electrons, so that is why it is paramagnetic. NiCO4 has also sp3 hybridization but no unpaired electrons, so that is why it is diamagnetic. Okay, again you need to draw the valence bond diagram and check. Okay, but for answer writing this much is fine, but if you want to verify you can just draw the valence bond diagram and check the answers. Next, FeH2O whole 6 is strongly paramagnetic, whereas FeCN6 3- is weakly paramagnetic. Okay, now magnetism depends on root over of n into n plus 2. So the more number of unpaired electrons, more paramagnetism is there. Less number of unpaired electrons, less paramagnetism will be there, right? So now if you see, we have FeH2O whole 6 has 5 unpaired electrons, so it is more paramagnetic. FeCN6 3- has 1 unpaired electron, so it is less paramagnetic. Okay. Next, color. A solution in NiH2O whole 6 2+ is green, but a solution of NiCN4 2- is colorless. So here also color is all about the number of unpaired electrons, right? So in NiH2O whole 6 there will be unpaired electron which can undergo DD transition, that is why it is colorful. So H2O is a weak field ligand in NiH2O whole 6. As a result, Ni2+ has unpaired electrons which can undergo DD transition, as a result of which Ni2+ appears green. Now NiCN4 2- is colorless due to the absence of unpaired electron in the complex. CO is a strong field ligand and produces electron pairing. Okay, so if there is a strong field ligand, pairing will take place, right? There will be no unpaired electron, no DD transition, no color. Okay. Next, FeCN6 4- and FeH2O whole 6 are different colors in dilute solution. Why? So the color depends on the amount of, you can say the amount of splitting, right? More is the splitting, more intense color you can see. But FeCN6 is a strong field ligand, so it has more splitting. Water is a weak field ligand, so it has less splitting. So based on that, different wavelength of light is absorbed, different wavelength of light is given out. So that is why it is a different colors are found. So you can see the color of a particular coordination compound depends on the magnitude of the crystal field splitting energy. In case of FeCN6 and FeH2O6, the colors differ because there is a difference in the CFSE. Now CN is a strong field ligand having a higher CFSE value as compared to CFSE value of water. Okay, because different lights will be observed, different colors will be observed. Next, explain the violet color of the complex TiH2O whole 6 on the basis of crystal field theory. So this is an NCERT question. Now see, coordination compounds exhibit color attributed to the crystal field theory which corresponds to the DD transition of the elements. In case of TiH2O whole 6, when light corresponding to the energy of the blue-green region is absorbed by the complex, it will excite the electron from T2G level to EG level, thus the complex will be violet in color. Okay, so you can see here TiH2O whole 6. Okay, so it has like this, electrons are present in the ground state. Okay, now when light, it absorbs light in the blue-green region, it gets excited and then it comes out and eliminates or emits light in the violet region, and that is why it is visible as violet. Okay. Next, anhydrous copper sulfate is white, but copper sulfate .5 H2O is blue in color. So this is very simple. Now due to heating, what happens when you heat this copper sulfate .5 H2O, water molecules evaporate, right? And there is no ligand left. Now if there is no ligand, there will be no DD splitting. Okay, d orbital splitting takes place only in the presence of the ligand. Now hence there is no splitting of d orbitals and there is no DD transition, so that is why it appears to be white. Okay. Next, what will be the correct order of the wavelength of absorption in the visible region of the following? Okay, so if you first see what is the ligand order, the order of the ligand or the strength of the ligand is water, NH3 and NO3. So that means water will split less, okay, NH3 will split more and NO3 will split maximum, right? So this is water, NH3 and NO3 minus. Right, now if here the splitting is more, here the energy will be more, wavelength will be less, because you know E is equal to Hc by lambda, right? So wavelength will be minimum here, so that is why NO2 will come the least one, then NH3 and then water. Okay, so this is NO2 minus. Clear? Next, question number 45, bonding in metal carbonyls, very important question. So this is very simple. The metal carbon bond in metal carbonyls is having both S and P character, or you can write have both sigma and pi bond. The MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into the vacant d orbital of the metal. So the sigma bond that is formed is due to the donation of electrons from the carbon to the d orbitals of the metal. Now there is also a pi bond formed. Okay, so this pi bond is due to the formation or donation of a pair of electrons from the filled d orbital of the metal to the empty pi star orbital of CO. Okay, so now because of this donation there is a pi bond formation takes place. Clear? Okay, next is your question number 46. Aqueous copper sulfate solution gives a green precipitate with aqueous potassium fluoride and a bright green solution with aqueous potassium chloride. So here you can see when aqueous copper sulfate reacts with fluorine you get CuF4, and when it reacts with 4-chlorine you get CuCl4, right? Now CuF4 color is your green and CuCl4 color is bright green. So what happens? This F minus replaces water, chlorine replaces H2O, and we get this color. Okay. Next, what is the coordination entity formed when excess of aqueous KCN is added to an aqueous solution of copper sulfate? Why is it that no precipitate of copper sulfide is obtained when H2S gas is passed through the solution? So you can see when copper is reacting with Cn, okay, so H2O will be replaced by Cn and you will get CuCN4. Now this has formed a complex. This copper is not available freely now. So the coordination species thus formed is very stable, and because Cn is a strong ligand. Now on passing H2S gas through this solution, CuS precipitate is not obtained because free Cu2 plus ions are not available. Now if you pass H2S gas, the copper 2 plus cannot go and react separately, right, because it is not available freely. Okay, it is already in the form of now complex. So that is why we do not find the precipitate of Cu2S. Clear? Okay, so now there are some points that I have discussed about the applications. You must do these applications because questions can be asked from here. So EDTA is used in hardness of water, right? Then this chlorophyll has the pigment of magnesium, hemoglobin has iron, right, and vitamin B12 has cobalt. So these also you should remember can be asked in MCQ. Then in photography, silver bromide is used, EDTA is used to treat lead poisoning, right, and then cisplatin is used for tumors. So these are certain uses that you should remember where it can be asked in the form of MCQs. Okay. Next, coming to the most important topics that you should revise from this particular chapter. I can say all the topics are very, very important, but still you should pay more importance on, I can say, nomenclature, isomerism, VBT, CFT. Okay, these are the more important topics, but yes, you should do all these topics. Okay. Okay, so students, I want to remind you about the PU2 Success Blueprint test series launched by Diksha. So it includes 12 mock tests, which includes like 4 part tests and 8 full length papers, and the first test will be released on 15th of December. Okay, and these tests will be covering PC, MB and CS, and you'll be getting exam focused questions, one shot revision videos, doubt clarification classes and video solutions with detailed explanation. Okay, so this test series is now available at a discounted price of $599. So make sure that you buy it at the earliest because the prices may go higher later, right? So students, this will definitely help you to boost your preparation. Make sure that you buy it. To register, you can go to the description section, the link is there, go purchase and then start your preparation. Okay, so one more thing. Yes, that was all about today's chapter, that is coordination compounds. I have given you so many questions, so please practice it, read those questions again and again. Nothing apart from these questions you will be getting, I can guarantee you that. So these are the 60 questions that you need to prepare for this chapter. Okay, so all the very best and see you soon in the next class.